So here it's saying that we need to record the charge Q at different voltages from 1, 2, 3, 4, 5, 6. So basically and this is going to be during 3-second terminals. So we will change the time base here and we will make it 3 seconds. And let's make the sampling 20 samples per second. Okay. And at this point we can start collect, but let's open the power supply and make it on 1 volt. You can see here it's 7, but we will make it on 1 volt. So it's 1 volt right now, and we'll start to collect. So you can see we have a signal of a charge of 10 nanocoulombs. It's constant during the 3-second terminal. At this point, we will go to experiment. We will store this on, and we will go here and change it to 1 volt. 1 volt. Okay? So you mark this reading as 1 volt reading. Then we will increase at this point the voltage into 2. It's 2 volts. Then we collect again. You can see a blue line at almost 19.7 nanocoulomb or 20 nanocoulomb. And we have the recording data here. Then we will store it, store the latest run. Then we will go to it and make it basically 2 volt. 2 volt. So for the sake of time, I will go directly, I will jump ahead. For example, I will make right now the voltage to be 4. For the sake of time. So it's 4 now. We will collect. So we have it here, 4 nanocoulombs. And we will store it again. We write down it's 4 volt. 4 volt. And we will increase the voltage to become 7. That's the final one, but you have to do it one by one. So it's 7 volts. Let's collect. So we can see here the orange lines going in the 70 nanocoulombs almost. And we'll do the same. We will say that store latest run and make this one to be 7 volt. And from here we have collected all the required data, and we can see that when we increase the voltage, the charges increases, and this is agrees with the rule which says that the amount of charge is equal to the multiplication of the capacitance multiplied by the voltage. Okay, and from these values we can actually find how much is the capacitance of the charge sensor itself. How much is capacitance, which is going to be 0.01 microcoulombs. Sorry, 0.01 microfarad. So we need to record, to save this data. So let's save it. Let's save it as a CSV, which is the Excel extension. So we have here the capacitor. Let's make this one part 1. So here we have the variable capacitor, we need to set it into 0.22 microfarad, which is basically 220 nanofarad, and we need to connect it in parallel with the capacitor itself. So let's get another 2 wires, one here, then connect it here with this banana cable. Then we have this one connected here. So right now the capacitor is connected parallel to the capacitance, or sorry, the resistor itself. Now we'll make a new sheet. So let's start a new one. So we have a new sheet, and you can see it's up to 60 seconds, but we will change this one to make it only up to 20 seconds of recording, and we will make the sampling to become 20 samples per second. Okay? So from here, right now the capacitor has charged, okay? And we will keep the power supply on 7 volts, and we will disconnect the circuit from the power supply. And as we said before, you remember this cable? When we said this cable is going to act as a switch, when we disconnect this one, it means we are disconnecting the power supply from the circuit, which makes the capacitor to discharge. Okay? So we will disconnect after 10 seconds. So let's see what's going to happen. So we will press collect. Right now we have 70 nanoseconds, nano columns, and it's going. Once it goes to 10, we will disconnect. So you can see the curve went down to almost 0 nano columns within certain time. And the objective here, we are going to get the time constant, and basically to predict the capacitance that we have used using the equation. So right now we have exponential decaying until the capacitor becomes fully discharged and has no charges at all. So at this point, we need to select only this distance, the duration of decaying, which is almost from here to here. Okay, this is almost the duration of decaying, and this is the one that we are going to do some analysis on it. Okay, so from here we are going to open an Excel sheet. Let's say this Excel sheet, let's say it's test. Open the Excel sheet, and from this one we need to confirm that we go to data and find that we have data analysis. Okay, but seeing that we don't have data analysis here on the screen, so that means we need to add it to the application. So we'll go back to file, we'll go to options, and we have here add ends. We press on it, then we'll have analysis tool pack, we'll press on it, then basically we are going to have we will add it, analysis tool pack, then we will say OK. So we can see it appears here on the data tab, and we have it here. Why? Because we need to do linear regression. So let's go back to the LoggerPro and select this amount of data, which is basically, it becomes shadowed here, and I'm going to press copy. Then I'll paste it here. So you can see here. So this is time. We will write it time. And this one, the charge on the capacitor itself. Then from here, we need to find two things. The natural log of the charge ratio of Q node over Q. Q node means the charge at the beginning. the charge at the beginning. So for us, this is Q naught, and this is T naught, or the time at the beginning. So we will find here the natural log of Q naught over Q. So basically, we're just going to say is equal to ln, then we have Q naught, which is this one. So let's copy this part. Let's let's copy this one. Then let's have equal to ln. Then we copy this one over the charge itself, the value of the charge. Then we close it, enter, so it's 0. Then when we extend this one, press here and extend. Right now we have all the values. So see, this one is 0. This one is over B4, B5, 6, 7, and so on. So this one, 28. So it's almost, there is no value here. Then we need to find T, the time, minus T naught, which basically T naught is 10.4. So this is equal to the value of the time minus T naught, which is 10.4. So it's here 0. So you can have it here. So this is the absolute time. Then we need to draw these together. Okay? And in this case, we will not use this part because it's not identified within the ln. So we need to draw this part only. So let's plot it. Insert, go to plots, have this one. And from here, we'll press select data. We will add. So this one, we are going to say that this charge, or like let's say ln Q naught over Q, and let's here find the data itself. And okay, and second, we need to make this one the horizontal axis to become the same value, which is, we are going to edit this one and we will select here. So we can see that this is the time, this is this one, and let's add C's, and we can change this one to ln Q naught over Q, and this one is time. And we can write also the value. Sorry, the unit itself. So from here, we are going to use the regression analysis to find the slope of this curve, so that we can find the value of 1 over tau, which is the time constant. So how are we going to do this? We will go to data analysis, linear regression. Let's go down, find linear regression or regression, and say OK. Then we need the y range, which is this one. Then we get the axis range, which is this one. Then we will press OK. Yeah. So we can see that there's another sheet that showed up, and it tells us how much is the coefficients, which is basically the x variable is 4.509. Okay. So the equation itself, it's basically y equal to 4.509 x plus C, which is the constant, which is minus 0.525. So this is the equation basically. And we can see that 4.5 is equal to 1 over tau, which means that tau itself, the time constant, is equal to 1 over 4.509, which is equal to 0.221 seconds. And time constant is equal to what? As you know, it's equal to RC, the resistance multiplied by the capacitance. And the capacitance in this case is the capacitance of the sensor parallel to the capacitance of the capacitor that we added basically. And the resistance, as we know, it's 1 mega ohm. So basically right now we have this capacitance, the resistance here. We can find the capacitance of the sensor as we can see it, or basically vice versa. We can find the capacity of this one if we know the capacitance of the sensor itself, which is 0.01 microfarad. So by doing this, you can find the tau from the curve that we got, which basically we got it from here, the decaying part. If you need to do another analysis, basically you can place another collect and you change the capacitor. At this point it's going to be, I think it was 0.1 nanofarad. So it's 0.1 microfarad, which is basically like this. And we can collect the data. Let's collect. We have to connect again the power supply to our circuit, which means that we have to connect these two together so that we can charge the capacitors. Then we press collect. You can see it's charged, and at 10 seconds we will disconnect. And we see here that the duration of decaying is much smaller, because basically time constant is equal to RC. So when we decrease the capacitor here, the time constant decreased, which is the time required to decrease or decay this signal. Okay, so you can see that this duration is smaller. And you can use it again to find, to predict the capacitor value or the charge sensor capacitor value. I hope this was clear to you, how to do the experiment, how to do the regression analysis to find the values and these coefficients. Basically this is the x variable, which is the slope, and this is the intercept, which is this part of the value, so we can get the line here. Also you can get like the line itself. If you press here and you right click and add trend, you can see this is a predicted line. Okay, and this line basically has these coefficients. So this is the end of our lab for today. I hope you enjoy the capacitor lab, and wait for me for the next one. And if you like the video, please like and subscribe, and see you soon.